Alright, so we are on to our second to last chapter. Don't worry, guys, we're almost done actually. If you think about it, we'll have just about a month left of classes and we'll be basically done. So, this is we're going to talk about solutions. Today's one is just going to be like an intro to solutions, some terminology, and defining what solutions are. Alright, so first, there's always two parts to a solution. When we talk about that, there's going to be one part what's called the solvent, and the other part is going to be the solute. Okay. The solvent is usually the substance that's more, whoops, go back real quick, sorry, that's more plentiful in a solution. Okay, so that's the one that occurs more in the solution, while the other part is going to be the solute. That's going to be one that's less plentiful in a solution. So like if you think about some examples, like an example would be like Gatorade. Okay, Gatorade, the substance that is most plentiful in that thing is water, actually. So that's going to be what the solvent is. Well, sugar is not as present as much as water, so it's going to be the solute. Same thing if you wanted to make salt water. You take a sample of salt water. Water is a solvent. Salt will be the solute. So solute is the one that's less plentiful. Solvent is more plentiful. Now we can also describe solutions in two ways right now in terms of how they're mixed. Those two ways is we're going to call it, one way is a homogeneous mixture, the other one's going to be called a heterogeneous mixture. And it means what it means if you know what homogeneous means, or homo, which is same. That means it's a mixture that is uniform in composition throughout. So this is going to be a mixture that's uniform. A good example of like a mixture that's uniform throughout is, again, Gatorade. Right, you take a sample of Gatorade, no matter if you're from a bottle, it's always going to be the same composition throughout. That's a homogeneous mixture. Now, related to homogeneous mixture, we can also call solutions that are miscible that form a homogeneous mixture. So like if I say water and Gatorade are miscible, that means they form a homogeneous mixture when you put them together now. Now the exact opposite of homogeneous is going to be what we'll call a heterogeneous mixture, which is a mixture with non-uniform composition. So this is if I mixed, let's say just an example, sand and water. Right, you mix sand and water, like here's your glass, here's your water, here's some sand at the bottom because it sinks. This is an uneven, non-uniform composition because if I take a sample of water from the top, it's just going to be water. It won't be sand until I go all the way down to the bottom. So that's an example of a heterogeneous. So homogeneous is a uniform one. So it's going to be the same composition no matter how many samples you take. Heterogeneous, that's going to be something with a different composition, so a non-uniform composition. Now, when we talk about solutions, we're first going to talk about suspensions or mechanical mixtures, right? So what a suspension is, that is a heterogeneous mixture, so a non-uniform, remember, mixture of two or more substances. Remember, it has to be at least two to be a suspension or solution. These substances don't dissolve in one another, okay? The particles will suspend, but they will eventually sink or float. When I say suspend, that means they'll be like in the middle of that solution, but eventually they'll either sink to the bottom or float to the top. And these are where particles do not break up in this suspension. Example like we just covered is sand and water, right? Remember, you put sand and water, here's your water, sand will eventually sink to the bottom. So that's a suspension or a mixture. Oil and water, they don't mix, but they still form a suspension. Okay? When you put oil and water, you're going to have a separation of liquids. One's going to be at the bottom, one's going to be at the top. They're not going to break up, but one eventually did sink. So suspensions or mixtures are heterogeneous. They're not uniform in composition of two or more substances, and they will never dissolve in one another. Okay, they'll eventually sink or float one of the substances. So now when we talk about solutions again, just straight solutions, these are always homogeneous mixtures. So compared to before, if I say a mixture or a suspension, that's always going to be heterogeneous. If I say a solution of something, that's a homogeneous mixture of two or more substances. Okay? And these actually do dissolve. So compared to before, they don't dissolve. These now do dissolve. And now remember, let's take the Gatorade sample. The amount of solute particles remains the same in all locations of the solution. So if you take a sample from one end of the solution or the other end, they'll be the same amount of solute particles. And these usually do break up to form ions or molecules. That's how they're allowed to dissolve. So this breakup allows the dissolution of one of those substances. Like an example is sugar and water, right? You put sugar and water, you mix it, eventually nothing will actually settle or float. It'll all be dissolved. Now, when we talk about solutions, there's ways you can describe about how much solute you put in there. The first one is a saturated solution. When I call something a saturated solution, that's when the solvent, so the thing that occurs the most, has dissolved the maximum amount of solute possible. So that means I've put in the most amount of solute I can to be dissolved in that solvent, okay, at a certain temperature. Obviously, a certain temperature won't change. But then after that maximum amount, some of those solid particles, will remain undissolved. So after I put so much in, there will be some undissolved. And you guys have seen this if you put sugar and water together, right? If you put enough sugar and water, not all the sugar actually dissolves. Some start settling at the bottom of the beaker. That's what we call a saturated solution, when you start seeing that sugar settle towards the bottom of the solution. And when we have a saturated solution, this is what we usually call what's an equilibrium, which means there are being solid particles dissolved at the same time the dissolved particle, that should be a comma, fall out of the solution. So as it's being dissolved, it's basically being undissolved at the same time. If we look at a picture of how this would actually kind of look, is again the sugar and water, right? You have this mixture in here, right? That's of sugar that's already been mixed, okay? But you've added too much and you have some now at the bottom. So this is a saturated solution. When you have excess sugar that's not dissolving at all, it's just settling at the bottom. The exact opposite is what we'll call an unsaturated solution. So this is when the solvent has dissolved less than the maximum amount of solution. No undissolved solution remains in the system. So it's just basically all been dissolved. So it's the exact opposite of a saturated. This is when everything has been dissolved, the solute, the solvent's dissolved it, we're good. So we got saturated, we got unsaturated to describe how they mix, okay? But we can also talk about solutions in terms of the phases. And then there's three different types of solutions we're going to talk about, but specifically we can categorize them a little bit more too. So let's go through these one by one. First is a gaseous solution. When I talk about a gaseous solution, I'm talking about a solution that has a solute gas phase and a solvent gas phase. And this is all air, basically, right? Oxygen, nitrogen mixed together, right? So anything that's in a gaseous phase will always mix evenly, actually, all the time. That's just how it works, because they're all in a gas phase. They have plenty of space to actually combine, right? Now, when we talk about liquid solutions, these all have liquids as their solvents, so now it changes the solute. And the first one is going to be a gas liquid solution. An example is your carbonated drinks, actually, where you have CO2, carbon dioxide, plus water. That's what gives its carbonation. So that's like a gas liquid solution where you have the carbon dioxide intermixing with water to create that carbonation, that fizz that you get from like a pop or even sparkling water, things like that. The second type of liquid solvent solution is liquid-liquid. So I mix two liquids together. And we'll talk more about this in a second, so we can talk a lot about. But an example is ethanol and water. So you want to mix ethanol and water together, you'll get a liquid-liquid solution. And then like we just talked about before, actually already so far, is now I can put a solid into a liquid, which is salt and water or sugar and water. So it's something that we've already talked about before. Then the last type of solution you can have is a solid solvent phase solution. So now the first part you have is solid-solid solution, which actually gets all alloys. Right? That's any metal you've seen where you mix like iron and copper together, or any two metals together. That's what an alloy is, remember? Any two metals. Right? They're combined to form something stronger usually. So all those are solid solutions actually. Another example of a solid solvent phase solution is a gas solid, which a really good example, which is the only one that we'll talk about, is hydrogen gas and metals. So hydrogen gas has the ability, so say like here's some metal particles that are like this. Hydrogen has the ability to fit right in between these metals and create a hydrogen infused metal essentially. So hydrogen gas has that special benefit where it can do that. But so gas is just basically air, any gases mixing together. Gas liquid is like your carbonated drinks. Solid is your alloys. Gas solid is really just hydrogen gas and any sort of metal. But we're going to talk about these two more real quick. Whoop, I'll skip this because we talked about it. So one example real quick of a liquid solution. Think of this as like dissolves like, which you've all observed this at one point. Now, one thing I remember is polar and nonpolar. Okay, remember polar means something has an electronegativity difference. Nonpolar means it doesn't have an electronegative difference. Okay, this is back when we drew molecules. What I mean by like dissolves like is they have to be of the same thing to dissolve one another. For example, if both solutions are polar, they will dissolve in each other. The exact same goes for if both solutions are nonpolar. They will dissolve in each other. A good example is water, H2O. Right? Remember we talked about this one a lot recently. As we talked about before, H2O was always a polar molecule. And let's say we look at something like NH3. NH3 was also polar, so if we actually had a solution of ammonia and a solution of water, these two would be, remember we called these miscible, which means if we mix them together, they form a homogeneous solution. Let's say we look at another example, H2O plus, let's look at something we'll call a hydro, remember the hydrocarbons were carbons and hydrogens, but put an OH at the end of it. This means, remember, this is an alcohol. If you see something like this at the end of a formula, it's usually an alcohol, which a majority of alcohols, this portion, are always polar. But if you remember, this portion of the molecule, the carbon hydrogen that we talked about before when we talked about the structure of molecules, anything carbon hydrogen was always nonpolar. So if these two mix together, a solution of water and ethanol, this would be slightly miscible actually, which means they will dissolve a little bit, but because of this nonpolar part, it won't dissolve as much. So what I'm saying is then, if we add more of this nonpolar part, it will become more and more not miscible. So let's say like if we have, let me erase this one. Let's say we added a longer hydrocarbon chain. So let's say we have CH3 parentheses C8, oops, CH, not CO, CH2, and 6 of those with OH. So now we have this very, very, very large non-polar region. So these two will not dissolve as well. Now, they may dissolve a little bit, remember, because of this polar part, but they still won't dissolve as well. So if I was comparing these two, this long hydrocarbon chain to this one will dissolve better than the top one. Okay, so you should be able to recognize that if I have a longer hydrocarbon chain, the less likely it will dissolve as well. Okay. Same thing if I add actually more OHs. So let's look if I change, let me erase all this actually. Let's say I mix water with something with 2 OHs. That's horrible. Let's rewrite that. Gosh, why do I keep doing that? So you want to think about which one of these would be more soluble or more miscible in water. Okay. This one they both have this about the same amount of, let me do a different color here, make it simple. They both have the same amount of hydrocarbon chain, right? 2 carbons, 2 carbons, they're about the same. But let's do black. This one has 1 polar region, while this one has 2 polar regions, which means it has more chances to mix with water. So this one will be more soluble with water compared to the second one because it has more spots for it to actually combine with it. So that is how something works if they are both polar or they both non-polar in dissolving. And then like we just talked about, if one now, the exact opposite occurs, if something is polar, but the other thing is non-polar, they won't dissolve. There has to be something all non-polar. Like say if I mixed water with CH4, these two will not mix, okay? Because there is no polarity on this guy. All right, one last thing and we'll be done. But the exact same can be talked about with solid liquid solutions. Okay, the same rule, where if you have if they're both polar, the solid and liquid, they'll dissolve within each other. But if they're both nonpolar, they will also dissolve within each other. But then again, if one is polar and one is nonpolar, they won't dissolve. And then another rule that goes along this is ionic compounds, which remember is a metal and a nonmetal, like NaCl, right, or magnesium chloride, right? Any one of those guys, those type of ionic compounds will dissolve in polar solvents, like for example, water or ethanol. Those guys are polar. Can't spell ethanol today. But the same rule kind of applies with like dissolves like, and also you have these ionic compounds. But those are solutions. So you'll have your homework. Let me know if you have any questions. Sorry this one went a little bit longer, but there was a lot of terminology to cover. So